There's a version of this story that spread fast online. A space telescope looked deep into the universe and found oxygen where it absolutely shouldn't exist. That sounds like a mistake, or at least an exaggeration. But the real story is actually more interesting and a lot more unsettling for astronomers. In March 2025, observations tied to the James Webb Space Telescope pointed to one of the most distant galaxies ever confirmed, known as JADES-GS-Z 14-0. This galaxy is so far away that we're seeing it as it was less than 300 million years after the Big Bang. That's extremely early, cosmically speaking. The universe had barely gotten started. Then came the part no one expected. Follow-up measurements detected oxygen in that galaxy. Not air, not something you could breathe, but oxygen atoms, heavy elements that only form inside stars and get spread out when those stars die. That creates a problem, because to get oxygen, you need stars. To get lots of oxygen, you need multiple generations of stars forming, living, exploding, and enriching their surroundings. And all of that takes time. Time this galaxy wasn't supposed to have. So the question isn't just, did Webb find oxygen? It's this: how did the universe manage to grow up so fast? Before oxygen entered the story, everything started with a faint patch of light that didn't look unusual at first glance. It came out of a deep survey called JADES, short for the JWST Advanced Deep Extragalactic Survey, where the James Webb Space Telescope spends hundreds of hours staring at tiny dark regions of the sky. The goal is simple. Look long enough and you start to see galaxies so distant that their light has been traveling toward us for over 13 billion years. That's where JADES-GS-Z 14-0 showed up. At first, it was just a candidate. Webb's infrared instruments picked up a source that seemed extremely red, which is exactly what you expect when light from a very distant galaxy gets stretched, shifted, by the expansion of the universe. This effect is called redshift, and it's one of the main tools astronomers use to measure distance. But here's the thing. Finding a candidate is not the same as confirming one. A lot of objects can mimic that signal. Dusty galaxies closer to us, for example, can also look red. So astronomers needed something more precise than just color. They needed a spectral fingerprint. That's where Webb's real power comes in. Instead of just taking images, it can split incoming light into a spectrum, basically stretching it out into its component wavelengths. And within that spectrum, certain patterns appear depending on what elements are present and how fast the object is moving away from us. When Webb analyzed the light from JADES-GS-Z 14-0, it found a very clear break in the spectrum, a sharp cutoff caused by hydrogen-absorbing light at specific wavelengths. This feature shifts depending on distance, and in this case, it pointed to an extreme redshift. Not just far, record-breaking far. This galaxy was confirmed to exist when the universe was under 300 million years old. To put that in perspective, that's about 2% of its current age. If the entire history of the universe were compressed into a single year, this galaxy would show up in the first week. That alone was already pushing expectations. Astronomers had models predicting that galaxies should exist this early, but not many, and not ones that are bright, structured, and easy to detect. Yet Webb kept finding them. Not just one, but a growing list of early galaxies that seemed more developed than expected. JADES-GS-Z 14-0 quickly stood out among them. It wasn't just distant, it was relatively luminous. That implies a significant amount of star formation already happening inside it. In other words, it wasn't a tiny, just-born system. It had activity, structure, energy output that suggested something substantial was already underway. Still, up to this point, everything was within the realm of surprising but manageable. A very early galaxy, that's fine. A bright one? Unexpected, but maybe rare. Astronomers could still explain it by tweaking models. Maybe star formation started earlier than we thought, or maybe some galaxies grew faster under the right conditions. Nothing was broken yet, but this is where the second step comes in, the one that turned a surprising discovery into a real problem. Because Webb didn't actually detect the oxygen. Get that, astronomers had to bring in another instrument, one that works very differently and sees a completely different part of the universe. They turned to Atacama Large Millimeter/Submillimeter Array. ALMA doesn't look at infrared light like Webb. It observes much longer wavelengths, millimeter and submillimeter radiation, coming from cold gas and specific atomic transitions. This makes it incredibly good at detecting certain elements, including ionized oxygen, in distant galaxies. Here's where things get precise. When oxygen atoms in space get energized by nearby stars, for example, they emit radiation at very specific wavelengths. These emissions act like fingerprints. If ALMA detects that signal and it lines up perfectly with the redshift measured by Webb, you can be confident you're looking at oxygen in that exact galaxy. That's exactly what happened. ALMA picked up a clear signal corresponding to ionized oxygen, and the redshift matched JADES JWST almost perfectly. Two independent systems observing completely different wavelengths, pointing to the same object at the same extreme distance. That's why astronomers take this seriously. This wasn't a vague hint, it wasn't a statistical anomaly, it was a cross-confirmed detection using two of the most powerful observatories on Earth and in space. And once that oxygen signal was locked in, the conversation changed immediately. Because now the galaxy wasn't just early, it was chemically evolved, which means everything that had to happen before that moment, star formation, stellar death, heavy element production, had to be compressed into an incredibly short window of time. And that's where things start to get uncomfortable. Not because the data is uncertain, but because it might be telling us the early universe was moving a lot faster than we thought. When people hear oxygen, it's almost impossible not to think about air, breathing, or life. But in astronomy, oxygen means something very different. It's not about habitability, it's about history. Oxygen is what astronomers call a heavy element. That doesn't mean it's physically heavy in your hand, it means anything heavier than hydrogen and helium. And that distinction matters because of how the universe started. Right after the Big Bang, the universe was incredibly simple. Almost all of the matter was hydrogen with a bit of helium and tiny traces of lithium. That's it. No carbon, no oxygen, no iron. None of the elements that make up planets, oceans, or living things today. Those elements had to be made later. The only place that happens naturally is inside stars. When a star forms, it begins fusing hydrogen into helium in its core. That process releases energy, which is what makes stars shine. But in more massive stars, fusion doesn't stop there. As the star evolves, it starts building heavier elements, carbon, oxygen, neon, and more, layer by layer in its core. Oxygen in particular forms during the later stages of a massive star's life, when temperatures and pressures get high enough for helium and carbon nuclei to fuse into oxygen. But here's the key detail. Those elements don't just drift out into space while the star is alive, they're locked inside. To release them, the star has to die. For massive stars, that death comes in the form of a supernova, an explosion so powerful that it blasts the star's outer layers into space. That debris carries newly formed elements, including oxygen, into the surrounding environment. Over time, that material mixes with gas clouds, which can then collapse to form new stars and galaxies that are richer in heavy elements. So, when astronomers detect oxygen in a galaxy, they're not just seeing an element. They're seeing evidence of an entire life cycle that has already happened. Stars formed, lived, created heavy elements, exploded, spread those elements, and enriched the galaxy. That's a long chain of events. And every step takes time. Even under fast conditions, you still need the first generation of stars to form out of pristine hydrogen and helium. Then those stars, especially the massive ones, live for a few million years before exploding. Then the enriched gas has to cool, mix, and form new stars again. Each loop builds up more heavy elements. This process is called chemical enrichment, and in the standard picture of cosmic evolution, it ramps up gradually. Early galaxies are expected to be chemically primitive, mostly hydrogen and helium, with only small amounts of heavier elements appearing later. That's why oxygen is such a powerful marker. It tells you how far along that process a galaxy is. If you find a galaxy with almost no oxygen, you're likely looking at something close to the first generation of star formation. If you find significant oxygen, it means multiple generations of stars have already come and gone. Now bring that back to JADES-GS-Z14-0. We're not looking at a galaxy billions of years into its evolution. We're looking at it less than 300 million years after the Big Bang. And yet, oxygen is already there. That implies the enrichment process didn't just start early, it had already progressed. Which forces a very specific question. How many cycles of star formation and death could realistically fit into that time window? Massive stars can live fast and die young, some in just a few million years. So in theory, you could squeeze in multiple generations if everything happens quickly. But that requires very efficient star formation, rapid recycling of gas, and conditions that favor the creation of massive stars early on. That combination isn't impossible, but it's not what most models expected to be common. And there's another layer to this. The oxygen detected by ALMA isn't just present. It's measurable in a way that suggests the galaxy isn't barely enriched. It's not sitting right at the threshold where you'd say, okay, maybe one generation of stars did this. It looks more developed than that. Which is why some astronomers describe galaxies like this as too mature for their age. Not in a vague sense, but in a very specific chemical sense. It's like walking into what should be a newly built city and finding fully developed infrastructure already in place. Roads, systems, layers of construction that imply a long history, even though the timeline says it shouldn't exist yet. Now, this doesn't mean physics is broken. It means our expectations about how quickly these processes can unfold might be off. Maybe the first stars formed earlier than we thought. Maybe they were more massive, lived shorter lives, and enriched their surroundings more efficiently. Maybe early galaxies were better at pulling in gas and forming stars at extreme rates. Or maybe we're just now seeing the fastest growing outliers, the rare systems that raced ahead of the average. But regardless of which explanation turns out to be correct, the presence of oxygen forces astronomers to confront something very concrete. By the time this galaxy's light began its journey to us, the universe had already gone through multiple rounds of stellar evolution. And that compresses a huge amount of cosmic history into a very small slice of time. That's why the oxygen matters. Not because it suggests life, but because it proves the universe was already doing complex multi-step chemistry much earlier than we were comfortable with. To understand why this discovery made astronomers pause, you have to look at what the expected timeline of the early universe actually looks like. Right after the Big Bang, the universe was hot, dense, and simple. Just hydrogen, helium, and a trace of lithium. Then it expanded and cooled. For a while, nothing much happened visually. No stars, no galaxies, just a dark, diffuse fog of gas. This period is often called the cosmic dark ages. Eventually, gravity started to pull that gas into denser regions. Over time, those regions collapsed enough to ignite the first stars. These are known as population 3 stars, the very first generation made entirely out of primordial material, with no heavy elements at all. Now here's the important part. These first stars were expected to be different from stars today. Because there were no heavy elements to help cool the gas, simulations suggest these stars were probably very massive, sometimes hundreds of times the mass of the Sun. That means they burned hot and lived short lives, sometimes only a few million years before exploding as supernovae. So far, so good. That actually helps the timeline because massive stars can enrich their surroundings quickly. They produce heavy elements like oxygen and release them into space relatively fast. But even with that advantage, there are still steps that have to happen in sequence. First, gas has to collapse into stars. Then those stars have to live out their lifetimes. Then they explode and release heavy elements. Then that enriched material has to mix with surrounding gas. Then new stars form out of that enriched gas. Each of those steps takes time, and more importantly, they don't all happen instantly across an entire galaxy. They happen in pockets, in bursts, in cycles. That's why most models predicted that early galaxies, especially within the first few 100 million years, would still be chemically primitive. You might get some enrichment locally, but not at levels that suggest widespread repeated star formation and recycling. Now place JADES-GS-Z14-0 on that timeline. We're seeing it less than 300 million years after the Big Bang. Let's be generous and say the very first stars in that region formed extremely early, maybe around 100 to 150 million years after the Big Bang. That already pushes toward the faster end of most estimates. From that point, you might get your first generation of massive stars living for a few million years, then exploding and releasing oxygen. Then you need time for that oxygen to mix into the surrounding gas and form a second generation of stars, then potentially repeat the process. All of this has to happen before the light we're now seeing left that galaxy. So the timeline gets tight very quickly. Even if each individual step can happen fast, stacking multiple generations back-to-back inside a window of maybe 100 to 150 million years starts to feel compressed. That's the tension. It's not that oxygen is impossible this early. It's that the amount and the implications of that oxygen suggest more history than the clock seems to allow. And there's another subtle issue: structure. This galaxy isn't just chemically interesting, it's also bright enough to detect clearly. That implies a substantial amount of star formation already underway. But building up that kind of luminosity also takes time. You need gas inflow, gravitational collapse, sustained star formation, and enough stars to collectively produce a strong signal. That's another layer of development happening alongside the chemical enrichment. So now you're stacking multiple fast processes: rapid star formation, rapid stellar evolution, rapid chemical enrichment, and rapid buildup of a luminous galaxy, all happening in parallel, very early on. Individually, each of these is possible. Together, within that time window, they start to push against what models were comfortably predicting. That's why discoveries like this don't immediately break cosmology, but they do stress test it. They force astronomers to ask, are our assumptions about early conditions too conservative? For example, maybe the first gas clouds collapsed more efficiently than expected. Maybe turbulence, radiation, and dark matter interactions created pockets where star formation was extremely intense right from the start. Or maybe early galaxies were better at holding onto gas, allowing them to recycle material quickly instead of losing it to space after supernova explosions. Another possibility is that the first stars were not just massive but extremely efficient at producing heavy elements, seeding their environments faster than standard models assume. There's also the chance that what we're seeing are rare extreme cases, the fastest evolving galaxies in the early universe, not the typical ones. In that case, the models might still be broadly correct, but they underestimated how early these outliers could appear. And that matters because Webb is not just finding one of these objects, it's finding several early galaxies that look brighter, more structured, or more evolved than expected. JADES-GS-Z14-0 with confirmed oxygen is one of the clearest examples, but it fits into a broader pattern that's been building since Webb started sending back data. That pattern is what's making astronomers pay attention, because when multiple independent observations start pointing in the same direction, it's less likely to be a fluke and more likely to be telling you something real about how the universe works. So the issue isn't that this galaxy shouldn't exist. It clearly does. The issue is that, according to older expectations, it should have had less time to become what it already is. And when the universe moves faster than your models predict, you don't throw out the data, you update the story. At this point, everything comes down to one thing: the clock. Astronomy is unusual in that looking farther away also means looking further back in time. Light doesn't arrive instantly, it travels. So when we observe a galaxy like JADES-GS-Z14-0, we're not seeing it as it is now. We're seeing it as it was when that light began its journey. In this case, that moment happened less than 300 million years after the Big Bang. That number is what creates the tension, because once you fix that point in time, everything else has to fit before it. Let's break that window down in a simple way. The Big Bang happens. The universe expands and cools. For tens of millions of years, there are no stars, just gas slowly clumping under gravity. Eventually, the first stars ignite. That already takes time, even under optimistic assumptions. Now imagine the clock reads roughly 100 to 150 million years. This is around when the earliest star formation might begin in certain regions. Not everywhere at once, just in the densest pockets where gravity wins quickly. From here, the process accelerates, but it still has structure. Massive stars form. They burn through their fuel rapidly. Some explode as supernovae within a few million years. That's fast, cosmically speaking. So yes, heavy elements like oxygen can start appearing relatively early. But here's the catch. One generation isn't enough to explain what we're seeing. A single wave of stars can produce some oxygen, but to build a galaxy that looks measurably enriched and bright enough to detect clearly, you likely need repeated cycles. That means new stars forming from already enriched gas, increasing the overall metallicity over time. So now we're stacking generations. Let's say first stars form at approximately 120 million years. They explode by approximately 125 to 130 million years. Gas begins to mix and collapse again. Second-generation stars form shortly after. Even in a best-case scenario, every loop eats into the timeline, and these steps don't happen instantly across an entire galaxy. They propagate, overlap, and compete with other processes like gas outflows and radiation pressure. Now jump forward to approximately 250 to 300 million years. That's when the light we see from JADES GSZ 14-0 was emitted. So everything, initial collapse, first stars, explosions, enrichment, rebuilding, and enough star formation to make the galaxy luminous, had to occur within roughly 100 to 150 million years of active evolution. That's tight. And the more mature the galaxy appears, the more pressure that puts on the timeline. Because maturity in astronomy isn't a vague label, it's measurable. It shows up in luminosity, structure, and, most importantly here, chemical composition. The oxygen detection tells us that this galaxy isn't sitting at the very beginning of its evolution. It's already partway through the process. That means the clock didn't just start early, it ran fast. Now, there's an important nuance here. Astronomers are not saying this is impossible. Physics allows for rapid star formation under the right conditions. Massive stars can evolve quickly. Gas can collapse efficiently if the environment is dense enough and cooling mechanisms are effective. So the issue isn't a violation of physical laws, it's that the default expectations, the average timelines built into many models, didn't predict this level of advancement so early, especially not in multiple observed cases. And that multiple part matters. If this were a single galaxy, you could argue it's an outlier, a rare region where everything happened unusually fast. But the James Webb Space Telescope has been finding several early galaxies that look brighter and more developed than expected. JADES-GS-Z 14-0 just happens to be one of the clearest examples because it has both an extreme distance and confirmed chemical enrichment through oxygen detection. That combination is hard to ignore. So now astronomers are faced with a few possibilities. One is that star formation began earlier than previously assumed. Maybe the first stars ignited closer to 50 to 80 million years after the Big Bang in some regions, which would give more breathing room for multiple generations. Another is that early galaxies formed stars at much higher rates than typical models suggest, turning gas into stars with extreme efficiency. There's also the possibility that feedback processes, like energy from supernovae, didn't slow things down as much as expected, allowing galaxies to keep forming stars instead of blowing their gas away. And then there's a broader idea. Maybe the early universe wasn't uniform in its pace of development. Some regions might have stayed quiet for longer, while others raced ahead, forming dense, rapidly evolving systems that we're now detecting because they're bright enough to stand out. If that's the case, Webb might be biased toward finding the overachievers, the galaxies that grew fast enough to be visible at extreme distances. But even that explanation doesn't fully remove the tension, because it still means those overachievers existed, and they reached a level of development very quickly. So the timeline problem isn't about a single contradiction. It's about compression. Too many steps, happening too quickly, inside a window that was expected to be more gradual. And when you compress cosmic history like that, you don't just adjust one number. You start rethinking how the earliest structures in the universe actually formed, evolved, and interacted, right from the beginning. At this point, the obvious question is, how do you actually prove there's oxygen in a galaxy this far away? Because at these distances, nothing is direct. You're not seeing shapes, clouds, or elements in any visual sense. You're working entirely with light that's been stretched, dimmed, and traveling for over 13 billion years. So the standard for evidence has to be extremely high. This is where the combination of the James Webb Space Telescope and the Atacama Large Millimeter/Submillimeter Array becomes crucial because they don't just repeat the same measurement. They approach the problem from completely different angles. Webb's role was to find and confirm the galaxy itself. Using its infrared instruments, it detected JADES-GS-Z 14-0 and measured its redshift through spectroscopy. That gave astronomers a very precise estimate of how far away it is, and therefore how far back in time we're seeing it. Once that distance is locked in, you know exactly where to look for any additional signals. And more importantly, you know how much those signals should be shifted due to the expansion of the universe. That's where ALMA comes in. Unlike Webb, ALMA doesn't operate in infrared. It observes much longer wavelengths, specifically in the millimeter and submillimeter range. This part of the spectrum is ideal for detecting emission lines from cold gas and certain ionized elements, including oxygen. Now, here's the key idea. Atoms don't emit light randomly. When an atom is excited, say by nearby star formation, it emits radiation at very specific, well-known wavelengths. These are called spectral lines, and each element has its own unique pattern. Oxygen has one of the most useful ones for this kind of work. A strong emission line from ionized oxygen, often referred to as O3. In a nearby galaxy, that emission would show up at a known wavelength. But for something as distant as JADES-GS-Z14-0, the expansion of the universe stretches that wavelength significantly, pushing it into the range that ALMA can detect. So the process works like this. First, Webb tells you, this galaxy is at this redshift. Its light has been stretched by this exact factor. Then ALMA looks for oxygen's signature, but not at its original wavelength. It looks where that signal should appear after being stretched by that same factor, and in this case, ALMA found it. A clear emission line, exactly where ionized oxygen should be, shifted precisely in line with Webb's redshift measurement. That alignment is what makes the detection strong, because now you have two independent confirmations. Webb identifies the galaxy and its distance. ALMA detects a specific element at that same distance. If those didn't match, the signal would be questionable. It could be from a closer object, background noise, or some unrelated source, but they do match. And that dramatically reduces the chances of a false detection. There's another layer of confidence here as well: signal clarity. Astronomers don't just look for a spike and call it a day. They analyze the strength of the signal, the noise level, and how statistically significant the detection is. In this case, the oxygen line stood out clearly enough to be taken seriously, not as a hint but as a measurable feature. That's why the phrasing around this discovery is careful but firm. They're not saying we might be seeing oxygen. They're saying the data is consistent with a real detection of ionized oxygen in this galaxy. And because the measurement comes from ALMA, one of the most sensitive arrays for this kind of observation, it carries weight. It's also worth noting that this kind of cross-confirmation is exactly how modern astronomy handles extreme claims. No single instrument is expected to prove everything on its own. Instead, different observatories specialize in different wavelengths and physical processes. When their results line up, the confidence increases significantly. That's what happened here. Webb didn't see oxygen directly. It set the stage by finding a galaxy at an extreme distance and measuring its redshift with high precision. ALMA then targeted that exact system and detected the oxygen signature in the appropriate wavelength range. Together they form a consistent picture. And that's why this result is being taken seriously by the scientific community. Because the oxygen isn't just an interpretation layered on top of uncertain data. It's a signal that shows up exactly where it should, in a galaxy whose distance is already well established. That's what makes the title true in a very specific sense. The oxygen is real, and once you accept that, you're left with the harder question. Not whether it's there, but how it got there so quickly. It's easy to focus on the word oxygen and treat it like the entire story. But for astronomers, oxygen is really just the entry point. The bigger issue is what it represents, because once you confirm oxygen in a galaxy like JADES-GS-Z14-0, you're not just adding one data point, you're uncovering a whole chain of processes that must have already taken place. Oxygen doesn't exist in isolation. If a galaxy has oxygen, it almost certainly has other heavy elements too: carbon, neon, maybe even traces of iron. That's because they're all produced through related processes inside stars. So detecting oxygen is like finding a clear marker that says this system has already moved beyond its initial, pristine state. In other words, this galaxy has history. And not just a little bit. Enough history to form stars, efficiently sustain star formation long enough for multiple generations, enrich its gas with heavy elements, and keep enough of that material to continue building structure. That combination is what makes this discovery expand beyond a single chemical detection. Because now you're not just asking, where did the oxygen come from? You're asking, how did this entire system evolve so quickly? And when you zoom out, that question touches almost every part of early galaxy formation. Start with star formation rates. For a galaxy to become chemically enriched this early, it likely had to form stars at a very high rate relative to its size. That means gas wasn't just sitting around, it was collapsing efficiently, converting into stars rapidly, and doing so in a sustained way. That's already pushing expectations. Then there's feedback, the process where stars, especially massive ones, inject energy back into their surroundings through radiation and supernova explosions. In many models, feedback slows things down. It heats gas, pushes it outward, and can temporarily shut off star formation. But if JADES-GS-Z14-0 managed to keep forming stars quickly despite that, it suggests either feedback was less disruptive than expected, or the galaxy was massive and dense enough to hold onto its gas anyway. Either option changes how we think about early galaxy environments. Then there's gas inflow. Galaxies don't grow in isolation. They pull in gas from their surroundings, especially along filament-like structures shaped by dark matter. If this galaxy was able to continuously draw in fresh gas, that could fuel rapid star formation and help explain its brightness and chemical state. But again, that requires efficiency and coordination between multiple processes happening at once. Now, layer on chemical enrichment. It's not enough to produce oxygen. That oxygen has to spread through the galaxy. It has to mix with existing gas, cool down, and become part of new star-forming regions. That mixing process is not instantaneous, so if we're seeing a measurable oxygen signal across the galaxy, it suggests that enrichment wasn't just local or isolated. It was already influencing the system on a larger scale, and all of this is happening within that tight early universe timeline. That's why astronomers don't look at this and say, interesting, oxygen showed up early. They look at it and say, this galaxy appears to have gone through a significant portion of its evolutionary path, much faster than expected. It's like discovering not just a single clue, but an entire sequence of events that had to occur before the moment you're observing. And there's an important shift that happens here. Before Webb, a lot of our understanding of early galaxies came from indirect observations and simulations. We had models that described how structure should form, how quickly stars should appear, and how chemical enrichment should build up over time. Those models weren't guesses. They were based on physics, tested against observations of later galaxies and refined over decades, but they also involved assumptions about initial conditions and efficiencies. What Webb and follow-up observations like ALMA are doing now is giving us direct data from that early period. And in several cases, that data is showing galaxies that look more active, more luminous, and more evolved than expected. JADES-GS-Z14-0 fits into that pattern. The oxygen detection just makes it harder to dismiss, because brightness alone can sometimes be explained. Maybe a galaxy is unusually efficient at forming stars, or maybe we're seeing a burst of activity. But chemical enrichment adds another layer. It says this isn't just a temporary spike. It's the result of processes that have already been running for some time. That's what elevates this from a surprising observation to something more fundamental. It suggests that, at least in some regions, the early universe was capable of building complex, chemically enriched systems very quickly. And if that's true, then the average picture of early galaxy formation might be missing something important, whether that's the speed of gas collapse, the nature of the first stars, or the way galaxies interact with their environment. There's also a broader implication here. Heavy elements are the raw material for planets. Now, this discovery does not mean planets existed this early in large numbers, and it definitely doesn't say anything about life. But it does push back the timeline for when the ingredients for planets became available. If oxygen, and by extension other heavy elements, are already present this early, then the building blocks for more complex structures were being assembled sooner than we thought. That doesn't rewrite the story of life in the universe, but it does shift the starting conditions. And all of that comes from detecting a single element in a single galaxy, which is why in astronomy, one well-measured signal can open up an entire cascade of new questions. because it's never just about the element. It's about everything that had to happen before it appeared. When astronomers try to describe galaxies like JADES-GS-Z14-0, they often reach for comparisons that make the timing issue easier to grasp. One of the most accurate ways they've put it is this: finding a galaxy like this is like walking into a nursery and seeing an adolescent. Not fully grown, not mature by today's standards, but clearly past the earlier stage, developed enough that you immediately notice something is off about the timeline. Because in that setting, everything is supposed to be a newborn. That's what the early universe was expected to look like. At less than 300 million years after the Big Bang, galaxies were supposed to be small, faint, and chemically simple. Think of them as just starting out, forming their first stars, beginning their structure with very little internal history, and many of them probably were. But JADES-GS-Z14-0 doesn't quite fit that description. It's not a fully evolved galaxy like the Milky Way, but it shows clear signs that it's already gone through multiple steps of development. It's bright enough to be detected clearly at extreme distance. It shows evidence of active star formation, and most importantly, it contains oxygen, meaning it has already experienced stellar processing. Put together, those traits make it look older, functionally older than its actual age suggests. That's what the adolescent idea captures. It's not about size alone, it's about state. Now, this analogy also helps clarify something important. This discovery doesn't mean everything is broken. If you walk into that nursery and see one adolescent, you don't conclude that human biology is wrong. You ask how that specific case happened. Was development unusually fast? Did something accelerate growth? Or are you misunderstanding the timeline for some individuals? That's exactly where astronomy is right now. Galaxies like this are not forcing scientists to throw out the entire model of cosmic evolution. But they are forcing a closer look at how flexible that model needs to be, because the early universe might not have been as uniform as we assumed. Instead of a smooth, gradual progression where all galaxies evolve at roughly similar rates, it may have been more uneven, some regions staying quiet longer, while others rapidly collapsed and formed stars at extreme rates. In that scenario, most galaxies would still look like newborns, but a few would race ahead and appear more developed, like JADES-GS-Z14-0. And here's where the James Webb Space Telescope plays a crucial role. Webb is incredibly sensitive to infrared light, which means it's especially good at detecting distant, bright galaxies. That creates a kind of observational bias. We're more likely to see the overachievers, the ones that formed stars early and became luminous enough to stand out. So it's possible that we're not seeing a representative sample of the early universe. We're seeing the standout cases. But even if that's true, it doesn't remove the challenge, because those standout cases still exist, and they still reached a level of development that requires explaining. The analogy also highlights something subtle about how astronomers think. They don't just categorize galaxies by age, they categorize them by properties: luminosity, mass, star formation rate, and chemical composition. So when they say a galaxy looks too mature, they're not making a vague judgment. They're comparing measurable traits against what models predict for that point in cosmic time. In this case, the mismatch shows up in multiple ways. The brightness suggests a high rate of star formation. The oxygen indicates prior generations of stars. The overall signal implies a system that has already undergone significant evolution. Each of those alone might be explainable. Together they reinforce the same conclusion. This galaxy progressed quickly, and when multiple independent indicators point in the same direction, it becomes harder to treat it as a coincidence. That's why the adolescent among babies analogy has stuck. It captures both the surprise and the restraint. It doesn't say the galaxy is impossible. It doesn't say our understanding is wrong. It just highlights the mismatch between expectation and observation. And that mismatch is exactly what drives science forward. Because once you accept that something developed faster than expected, you start looking for mechanisms that could make that happen. Earlier star formation, more efficient gas collapse, different properties of the first stars, or environmental conditions that favor rapid growth. Each of those possibilities can be tested, And that's where this stops being just a surprising headline and becomes an active area of research, because the goal isn't to defend old expectations, it's to update them based on what the universe is actually showing us. And right now, at least in some cases, it's showing us that growth in the early universe could happen faster and reach further than we assumed. To really understand why this discovery stands out, it helps to rewind the story, not from our point of view, but from the galaxies. Take JADES-GS-Z14-0 and imagine everything that had to happen before the light we're seeing today was emitted. Because by the time that light left the galaxy, the oxygen was already there. The stars responsible for creating it had already lived and died. The galaxy had already reached a level of brightness and structure that made it detectable across billions of light years. So let's rebuild that sequence step by step. Start with a region of the early universe, just gas, mostly hydrogen and helium, with tiny fluctuations in density left over from the Big Bang. Gravity begins to pull slightly denser regions inward. Dark matter helps shape this process by forming gravitational wells that ordinary matter falls into. Over time, gas accumulates in these regions, heating up as it collapses. At some point, conditions become extreme enough for the first stars to ignite. These first stars are likely very massive. Without heavy elements to cool the gas efficiently, the collapsing clouds don't fragment as much, leading to the formation of large stars rather than many small ones. These stars burn intensely and live fast. Within a few million years, they begin to die, some collapsing directly into black holes, others exploding as supernovae. It's in these explosions that oxygen is created and released. So now, for the first time, the surrounding gas is no longer pristine. It contains heavier elements. But that's not enough. That enriched material has to spread. Supernova explosions push gas outward, mixing it with the surrounding medium. Some of that gas escapes, but some of it remains bound to the growing galaxy, especially if the gravitational pull is strong enough. Then comes the next step. The gas cools again. Cooling is crucial because hot gas resists collapse. Once it cools, gravity can pull it back together into new dense regions. And now, those regions are different from the first ones. They contain heavy elements. That changes how stars form. With oxygen and other elements present, gas can radiate energy more efficiently, fragment more easily, and form stars with a wider range of masses, including smaller, longer-lived stars. So the second generation of stars begins to form. And this is where the cycle starts to build momentum. More stars leads to more heavy elements, leads to more efficient cooling, leads to more star formation. If conditions are right, this can turn into a rapid feedback loop, not in the sense of shutting things down, but in accelerating the complexity of the system. Now add another layer, gas inflow. The galaxy isn't isolated. It's connected to the larger cosmic web, filament-like structures of matter that funnel gas into forming galaxies. If JADES-GS-Z14-0 sits in a region with strong inflow, it could continuously receive fresh material, fueling ongoing star formation and helping it grow quickly. At the same time, star formation inside the galaxy is producing radiation and supernova explosions that push against that inflow. So there's a balance: gravity pulling gas inward, feedback pushing gas outward, cooling allowing collapse to restart. Somehow in this system, that balance allowed sustained growth. Not just a brief burst, but enough activity to build a significant population of stars, produce and distribute oxygen, and generate the luminosity we now detect. And all of this had to happen before the light we're seeing left the galaxy. That's the key point. We're not watching these steps unfold. We're seeing the result after they've already occurred. It's like arriving at a construction site and seeing a partially built structure. You don't witness the earlier stages, but you can infer them from what's already there. And in this case, the structure is telling us that multiple phases of development have already taken place. Now, compress that entire sequence into less than 300 million years. More realistically, into a smaller window within that, because the earliest part of that time is still spent forming the first stars. That's where the pressure comes from. Not from any single step, but from fitting all of them together into a limited time frame. And there's another subtle implication here. Each of these processes, collapse, star formation, supernova feedback, chemical mixing, gas inflow, is governed by physical laws we understand reasonably well. But how they interact in extreme environments like the very early universe is still an active area of research. Small changes in initial conditions can lead to big differences in outcomes. For example, slightly higher density could trigger earlier collapse. More efficient cooling could accelerate star formation. Stronger gravitational wells could retain more enriched gas. If several of these factors align, you could get a system that evolves much faster than average. And that may be what we're seeing, but even if that's the case, it still means the early universe was capable of producing these fast-track galaxies. Which brings us back to the bigger question, not just how did this galaxy form, but how common was this kind of rapid evolution? Because if JADES-GS-Z14-0 is rare, it's an extreme example worth studying. But if more galaxies like it keep showing up as the James Webb Space Telescope continues observing, then we're looking at a pattern. And patterns are what force models to change, so by the time that ancient light began its journey, the hard work was already done. The stars had formed, the oxygen had been created, the galaxy had taken shape. And all we're seeing now is the snapshot that proves it happened. At this point, it might sound like discoveries like JADES-GS-Z14-0 are about to break everything we thought we knew about the early universe. They're not. But they are putting pressure on very specific parts of the model, especially the assumptions about timing, efficiency, and how quickly complexity can build. The core framework of cosmology is still holding up. The Big Bang model still explains the expansion of the universe, the cosmic microwave background, and the large-scale distribution of galaxies. None of that is threatened by finding oxygen in an early galaxy. What's being tested is the detail layer, how structure forms inside that framework. In other words, not did the universe begin this way, but how fast did the first galaxies grow and under what conditions? And that's where things are shifting. Before the James Webb Space Telescope, astronomers relied heavily on simulations to model early galaxy formation. These simulations included known physics, gravity, gas dynamics, radiation, and feedback, but they still had to make assumptions about things like star formation efficiency, the mass distribution of the first stars, how strongly supernovae push gas out of galaxies, how quickly gas cools and collapses again. Those assumptions were tuned to match observations of later galaxies because that's what we had the most data for. Now Webb is giving us direct observations from much earlier times, and in several cases the universe looks more active than those simulations predicted. So the question becomes, do we need entirely new physics? Right now the answer is probably no. There's no clear evidence that the laws of physics are different in the early universe. Instead, it's more likely that the parameters within those laws, how efficiently certain processes happen, need to be adjusted. For example, star formation efficiency might have been higher in the early universe. Gas could have collapsed into stars more quickly, especially in dense regions. Another possibility is that the first stars were not just massive but extremely effective at enriching their surroundings, producing large amounts of heavy elements in a short time. There's also the role of environment. Galaxies don't form in isolation. Some regions of the universe are denser than others, connected by filaments of matter that can funnel gas into forming systems. If JADES-GS-Z14-0 sits in one of these high-density regions, it could have had access to a steady supply of fuel, allowing it to grow rapidly. Then there's feedback. In many models, feedback from stars, especially supernova explosions, acts as a brake. It heats gas, pushes it outward, and slows down further star formation. But if feedback was less disruptive than expected, or if early galaxies were better at holding onto their gas, then star formation could continue more smoothly and rapidly. Each of these adjustments keeps the same underlying physics, but changes how quickly the system evolves, and that's usually how science responds to new data. You don't throw out a working framework unless you absolutely have to. You refine it. Now, there is a more extreme possibility, but it's not the leading one. Some researchers have explored whether more fundamental changes, like differences in dark matter behavior or early energy injection, could play a role in accelerating structure formation. But those ideas require strong evidence because they affect many other parts of cosmology. So far, observations like this don't demand that level of revision. They point more toward faster, more efficient galaxy formation within the existing framework. There's also another important factor: selection bias. The galaxies we can detect at these extreme distances are the brightest ones. That means we're naturally seeing the most active, fastest-growing systems. So it's possible that JADES-GS-Z14-0 is not typical. It's just one of the early universe's overachievers. If that's the case, then the average galaxy might still follow the slower, more gradual evolution predicted by earlier models. But even then, those models still need to account for the existence of these extreme cases, because once you've observed them, they're part of the universe's behavior, and there's a pattern forming. Webb hasn't just found one surprising galaxy, it has found several early galaxies that appear brighter, more massive, or more evolved than expected. JADES-GS-Z14-0 stands out because of the confirmed oxygen, but it's part of a broader trend, and trends are harder to ignore than isolated anomalies. So where does that leave us? In a position that's actually very familiar in science. The big picture is intact, but the details are being sharpened. Astronomers are now updating simulations, testing new parameter ranges, and looking for additional observations that can confirm whether these fast-evolving galaxies are rare exceptions or a common feature of the early universe. Future observations, both from Webb and from facilities like Atacama Large Millimeter/Submillimeter Array, will help answer that. More galaxies, more measurements of elements like oxygen, better statistics. That's how the picture becomes clearer. So the models don't collapse under this discovery, but they do shift, because the universe just showed us that, at least in some places, it was capable of building complexity faster than we expected, and now the job is to understand exactly how it pulled that off. By now, it might seem like JADES-GS-Z14-0 is just one strange case, an outlier that happened to evolve unusually fast. But it's not alone. Since it began full science operations, the James Webb Space Telescope has been consistently uncovering galaxies in the early universe that look brighter, more massive, or more developed than many pre-2022 models expected. That pattern is what turns this from an interesting discovery into something more important. Because when multiple observations point in the same direction, you're no longer dealing with a coincidence, you're looking at a trend that needs explaining. So why does Webb keep finding these too mature galaxies? Part of the answer comes down to what Webb is uniquely good at. Unlike previous telescopes, Webb is optimized for infrared light. That matters because light from extremely distant galaxies gets stretched into the infrared range as the universe expands. So where older telescopes struggled to detect these objects, Webb can see them clearly. But sensitivity alone doesn't explain the maturity. It explains why we can find distant galaxies, but not why those galaxies look more developed than expected. For that, you have to look at a combination of observational bias and real physical processes. Start with bias. Webb is most likely to detect galaxies that are bright, and brightness at these distances usually means active star formation. So right away, we're not seeing a random sample of early galaxies. We're seeing the ones that are forming stars rapidly enough to stand out. That skews the picture toward the most extreme systems. If the early universe had a mix of quiet, slowly evolving galaxies and a few fast-growing ones, Webb would preferentially pick up the fast-growers. That alone could explain part of the pattern, but not all of it. Because even among bright galaxies, the level of development we're seeing is still pushing expectations. So the next layer is physical. There are several ways the early universe could produce galaxies that evolve quickly. 1. Early start times. If star formation began earlier than previously assumed, closer to 50 to 80 million years after the Big Bang in some regions, then galaxies would have more time to build up mass and heavy elements by the time we observe them. Even a shift of a few tens of millions of years makes a difference at these timescales. 2. High-density environments. And galaxies forming in dense regions of the cosmic web can grow faster because they have access to more gas. Continuous inflow along filaments can fuel sustained star formation, allowing these systems to build up quickly. 3. Efficient gas cooling. Once heavy elements like oxygen are present, gas can cool more effectively. That makes it easier for gravity to pull it into new stars, accelerating the cycle of star formation and enrichment. This creates a feedback loop. More stars leads to more heavy elements, leads to better cooling, leads to even more stars 4. Less disruptive feedback. If early supernovae and stellar radiation didn't blow gas out of galaxies as effectively as models assumed, then galaxies could retain more of their material and keep forming stars without long interruptions. That would allow for smoother, faster growth. 5. Top-heavy star formation. If the first generations of stars were dominated by very massive stars, they would produce large amounts of energy and heavy elements quickly. That could jumpstart chemical enrichment earlier than expected. Now, none of these ideas are new on their own. What's new is that Webb is providing direct evidence that some combination of them must be happening because we're seeing the results. And it's not just JADES-GS-Z 14-0. Multiple early galaxies have shown higher than expected luminosities, larger inferred stellar masses, signs of structured formation, and in some cases, early chemical enrichment. Each observation adds weight to the idea that the early universe was capable of rapid galaxy growth. There's also an important shift happening in how astronomers interpret these findings. Before Webb, many models were calibrated using later observations, galaxies that had billions of years to evolve. Those models were then extended backward to predict what the earliest galaxies should look like. Now, we're going the other direction. We're observing the earliest galaxies directly and using that data to refine the models going forward. That's a more powerful approach, but it also means confronting surprises. And Webb has delivered several, but it's worth keeping perspective. Too mature doesn't mean impossible. It means the distribution of galaxy properties at early times is broader than expected. Some galaxies may still follow the slower, gradual path. Others may evolve rapidly under the right conditions. What Webb is revealing is the range of possibilities, and that range appears to include systems that can form stars early, build mass quickly, and undergo chemical enrichment in a short time. JADES-GS-Z 14-0 is one of the clearest examples because it combines all of these traits and adds confirmed oxygen on top. That's why it stands out. It doesn't just fit the pattern, it strengthens it. And as Webb continues observing, the key question becomes more precise. Are these fast-evolving galaxies rare exceptions, or are they a common feature of the early universe that we simply didn't have the tools to see before? Because the answer to that will determine whether we're making small adjustments to our models, or rewriting how the first galaxies grew altogether. When a result like this spreads beyond the scientific community, the details tend to get simplified and sometimes distorted. The phrase oxygen detected in the early universe sounds dramatic, and it's easy to jump to conclusions that don't actually match what astronomers found. So it's worth clearing up the most common misunderstandings because they change how you interpret the entire discovery. First, this is not about breathable oxygen. The oxygen detected in JADES-GS-Z 14-0 is not the kind you and I rely on. It's not part of an atmosphere, and it's not forming clouds you could pass through. What's being detected is ionized oxygen, individual atoms that have lost electrons and are emitting radiation at very specific wavelengths. This is a signature of energetic environments, usually driven by star formation. It tells you that stars are heating and exciting the surrounding gas. So when astronomers say oxygen, they mean a chemical tracer of stellar processes, not air, not life, and not something you could breathe. Second, this is not evidence of life. Oxygen on Earth is strongly associated with biology, but that connection only works in a very specific context: planetary atmospheres shaped by living organisms. In deep space, oxygen is just another product of nuclear fusion inside stars. It shows up anywhere massive stars have lived and died, whether life is present or not. So detecting oxygen in a distant galaxy says nothing about biology. It only tells us that stars have already been through part of their life cycle. Third, this does not contradict the Big Bang. This is one of the biggest misconceptions. Some headlines frame discoveries like this as if they challenge the entire origin of the universe. They don't. The Big Bang model explains the large-scale expansion of the universe, the cosmic microwave background, and the initial composition of matter. None of that is affected by finding oxygen in an early galaxy. What is being tested is the timeline of structure formation, how quickly galaxies formed stars and produced heavy elements after the Big Bang. That's a refinement of the model, not a contradiction. Fourth, Webb did not see oxygen directly in the way people imagine. The James Webb Space Telescope identified the galaxy and measured its distance through infrared spectroscopy. The actual detection of oxygen came from the Atacama Large Millimeter/Submillimeter Array, which observed a specific emission line associated with ionized oxygen. So this is a combined result. Two different observatories working at different wavelengths produced measurements that line up. That's why the detection is taken seriously. It's not based on a single ambiguous signal. Fifth, this doesn't mean the entire early universe was like this. It's tempting to assume that if one galaxy looks chemically evolved, then all early galaxies must have been the same. But that's not how observations work. We're currently limited to detecting the brightest and most active systems at these extreme distances. So what we're seeing may be the fastest growing galaxies, the ones that stand out. There could be many other galaxies at the same time that are faint, less evolved, and closer to what earlier models predicted. We just can't see them yet. So this discovery expands the range of what's possible, but it doesn't automatically redefine the average case. Sixth, this is not a mistake or a glitch in the data. Whenever a surprising result appears, there's a natural instinct to assume something went wrong. But in this case, the oxygen signal has been cross-checked. The redshift measured by Webb matches the emission line detected by ALMA. The signal stands out above the noise. Independent teams have analyzed the data. That doesn't mean it's beyond further scrutiny. Science always rechecks results, but it does mean this isn't being treated as a fluke. It's a serious observation that fits consistently within the data. And finally, this is not the end of the story. It's the beginning of a more detailed phase of understanding. Discoveries like this don't close questions. They open them. They push astronomers to gather more data, refine models, and test new ideas about how the early universe behaved. So the real takeaway isn't that something impossible happened. It's that something happened earlier and more efficiently than we expected. And once you strip away the misconceptions, that's what makes this discovery interesting. Not because it breaks the universe, but because it reveals that the universe may have been more capable, more active, and more complex in its earliest moments than we gave it credit for. Even after clearing up the misconceptions, it's easy to downplay this discovery. No life, no atmospheres, just atoms in space. So why does it matter so much? Because oxygen is not just another element. It's one of the clearest markers of how far a galaxy has progressed through its internal evolution. When astronomers look at a system like JADES-GS-Z14-0, they're not just asking what's there, they're asking what must have already happened to produce what's there. And oxygen answers that question in a very direct way. To get oxygen, you need stars that are massive enough to fuse heavier elements, short-lived enough to evolve quickly, and explosive enough to distribute those elements into space. That alone already tells you something about the type of stellar population that existed in this galaxy. But it goes further. The presence of oxygen means the galaxy has moved beyond its first generation of stars. The earlier stars, often called Population 3, would have formed from pristine hydrogen and helium. They would produce heavy elements when they died, but the environment around them would initially be untouched. So when you detect oxygen in a galaxy, you're looking at a system that has already gone through at least one full cycle of star formation and death, and likely more. That's what makes oxygen a timeline marker. It tells you that the galaxy isn't just forming stars, it's recycling material. Gas becomes stars. Stars create heavy elements. Those elements return to the gas. And the cycle continues. Each loop increases the complexity of the system. Now bring that back to the early universe. At less than 300 million years after the Big Bang, you might expect galaxies to still be near the beginning of that cycle. But JADES-GS-Z14-0 isn't. It's already partway through. And that has consequences beyond just one galaxy, because once heavy elements exist, they change how galaxies behave. They affect cooling. Gas with heavy elements can radiate energy more efficiently. That allows it to collapse faster, form stars more easily, and build structure more quickly. So oxygen doesn't just mark past activity, it also influences future evolution. It accelerates the process. That's why detecting oxygen this early is like finding evidence that the system has already crossed a threshold. Before that threshold, galaxy formation is slower and more limited. After it, things can ramp up. There's also a structural implication. When gas can cool efficiently, it doesn't just form stars randomly. It can settle into more organized structures, disks, clumps, and denser regions that shape how the galaxy evolves over time. So oxygen indirectly connects to morphology, the physical form of galaxies. And then there's the broader cosmic context. Heavy elements like oxygen are the building blocks for planets. Again, this does not mean planets were common this early, and it says nothing about life. But it does mean the raw ingredients for solid structures, rocks, minerals, eventually planetary systems, were starting to appear. That pushes back the timeline for when the universe became chemically capable of forming complex objects. It's a shift in the starting conditions. Instead of a long delay before heavy elements become available, we now have evidence that at least some regions of the universe reach that stage quickly. And that changes how we think about everything that comes after. Not in a dramatic, headline-driven way, but in a foundational way. Because the early presence of oxygen suggests that the universe didn't spend as long in a simple, hydrogen-dominated phase as we once assumed, at least not everywhere. Some regions moved on faster. And that introduces variability into the timeline. Different parts of the universe could be at very different stages of development at the same cosmic time. That's an important shift. It means the early universe wasn't just a uniform progression from simple to complex. It may have been a mix, some regions still forming their first stars, others already undergoing multiple cycles of enrichment. JADES-GS-Z 14-0 falls into that second category. And because we can measure that through oxygen, we're not guessing. We're reading the chemical record left behind. That's why oxygen matters even without any connection to life. It's not about biology, it's about chronology. It tells us where a galaxy sits in its evolutionary path, and in this case, it's further along than expected for its age. And once you establish that, the rest of the questions follow naturally. How did it get there so fast? How common is that pathway? And what does that say about the early universe as a whole? Those are the questions that make this discovery important, because they don't just apply to one galaxy. They apply to the entire timeline of cosmic evolution. For a long time, the early universe was pictured as a slow transition. After the Big Bang, there's a long quiet period. Then the first stars appear, then galaxies begin to form. Then gradually, over hundreds of millions of years, those galaxies become brighter, more structured, and chemically enriched. That picture wasn't random. It came from simulations, indirect observations, and what we could infer from later galaxies looking backward. But observations tied to JADES-GS-Z 14-0 are forcing a shift in that narrative. Not a complete rewrite, but a change in how fast things can happen and how uneven that process might be. Because what we're seeing now suggests that cosmic dawn, the era when the first stars and galaxies lit up the universe, may not have been a gentle, uniform ramp. In at least some regions, it may have been fast and chaotic. Instead of small stars to slow growth to gradual enrichment. We may be looking at early collapse to rapid star formation to quick enrichment to accelerated galaxy buildup. That's a very different pace, and it affects how we interpret the first few 100 million years of cosmic history. Start with timing. If galaxies like JADES GS-Z already contain oxygen and show strong star formation less than 300 million years after the Big Bang, then the processes that lead to complexity must have started earlier than expected. That shifts the beginning of meaningful structure formation closer to the Big Bang itself. Even a shift of tens of millions of years matters here, because everything is happening on compressed timescales. Then there's the question of uniformity. Older models often treated the early universe as broadly similar across large regions. Differences existed, but the overall pace of evolution was expected to be comparable. Now, it looks like that may not be true. Some regions may have evolved quickly, forming dense, active galaxies early. Others may have lagged behind, remaining faint and chemically simple for longer. That creates a more uneven picture of cosmic dawn. a mix of fast and slow development happening at the same time. And that has observational consequences. It means when we look back with the James Webb Space Telescope, we're not just seeing the early universe as a single state. We're sampling a range of evolutionary stages that existed simultaneously. Some galaxies are just getting started. Others, like JADES-GS-Z14-0, are already well into their development. That complicates the story, but it also makes it more accurate, because the universe doesn't evolve in lockstep. It evolves through local conditions, density, gas availability, gravitational structure, each region following its own path within the same overall framework. There's also an important implication for ionization. This is the period when the first stars and galaxies produced enough radiation to ionize the surrounding hydrogen, effectively ending the cosmic dark ages. If galaxies formed stars earlier and more efficiently than expected, they could have contributed to reionization sooner and more strongly. That could help explain how the universe transitioned from neutral to ionized within the observed time frame. So discoveries like this don't just affect galaxy formation, they tie into larger cosmic milestones. And then there's the question of how quickly complexity emerges. Once heavy elements like oxygen appear, the conditions for further structure formation improve. Cooling becomes more efficient. Star formation becomes easier. Systems can build up faster. So if that threshold is reached earlier, everything downstream can accelerate. It's like moving the starting line forward in a race. The entire sequence shifts. Now, it's important to stay grounded here. This doesn't mean the early universe was fully developed or filled with mature galaxies. Most regions were still in early stages, but it does mean that the upper limit of how fast galaxies can evolve is higher than we thought. And that matters for models. Because models don't just need to explain the average case, they need to account for the full range of observed behavior. Right now, that range includes galaxies that reach significant levels of brightness and chemical enrichment very early. JADES GSZ14-0 is one of the clearest examples because of the oxygen detection, but it fits into a broader pattern that Webb is revealing. And that pattern is what's reshaping the story of cosmic dawn. Not by discarding the old framework, but by adding a new layer. The early universe wasn't just gradually turning on. In some places, it was already running at high speed. At this point, the discovery tied to JADES-GS-Z14-0 has done its job. It hasn't answered the big questions, it's sharpened them. Now the focus shifts from what we found to how we test it. Because a single galaxy, even one this extreme, isn't enough to map out the full behavior of the early universe. Astronomers need patterns, statistics, repeated signals across multiple systems. So the next phase is very targeted. First, find more galaxies like this. The James Webb Space Telescope is already doing this through deep field surveys, long exposures of small patches of sky designed to reveal extremely distant objects. The goal is simple. Build a larger sample of galaxies at similar distances and see how many of them show signs of rapid evolution. Are oxygen-rich systems rare exceptions? Or are they common enough to suggest that fast chemical enrichment was normal in certain environments? That's a critical distinction. Second, measure more elements, not just oxygen. Oxygen is a strong tracer, but it's only one piece of the chemical picture. Astronomers want to detect other elements, carbon, nitrogen, neon, because each one adds more information about the types of stars that formed and the processes that shaped the galaxy. Different elements are produced in different kinds of stars and released through different mechanisms. So by mapping multiple elements, researchers can reconstruct the history of star formation in much more detail. This is where facilities like the Atacama Large Millimeter/Submillimeter Array become even more important, because they specialize in detecting these kinds of emission lines. Third, refine star formation rates. Right now, estimates of how quickly these early galaxies formed stars come with uncertainties. Webb provides strong constraints, but astronomers want more precise measurements. How intense were these star-forming episodes? Were they short bursts or sustained over tens of millions of years? That distinction matters because a brief extreme burst might explain high luminosity without requiring long-term stability. A sustained rate, on the other hand, implies a more stable and efficient system. Fourth, improve simulations. This is where theory catches up with observation. Researchers are already updating galaxy formation models to test different scenarios, earlier onset of star formation, higher efficiency in converting gas into stars, different assumptions about how gas flows into galaxies, variations in how strongly supernova feedback disrupts star formation. The goal isn't to force models to match one galaxy, it's to create models that naturally produce the range of galaxies we're now observing, including the fast-evolving ones. Fifth, look for even earlier systems. If JADES-GS-Z14-0 already shows oxygen at under 300 million years. The obvious next question is, what about galaxies at 200 million years? Or 150? Do they also show signs of enrichment? Or do we finally reach a point where galaxies look truly pristine? That boundary, where heavy elements first appear, is one of the most important markers in cosmic history, and Webb is pushing closer to it with every observation. Sixth, connect to large-scale structure. Astronomers also want to understand the environments these galaxies live in. Are fast-evolving systems clustered in dense regions of the cosmic web? Do they sit at intersections of gas-rich filaments? If so, that would support the idea that environment plays a major role in accelerating galaxy growth. This requires mapping not just individual galaxies but their surroundings, something that will become clearer as more data accumulates. And finally, check consistency across methods. The oxygen detection here is strong because it combines independent measurements. Future work will continue this approach using different instruments, wavelengths, and techniques to confirm results. Because in astronomy, especially at extreme distances, confidence comes from agreement across multiple lines of evidence. So the path forward isn't about one dramatic breakthrough, it's about building a detailed, consistent picture. More galaxies, more elements, better measurements, stronger models. That's how the story evolves. And right now, that story is moving in a clear direction. The early universe was capable of forming complex, chemically enriched galaxies faster than we expected. Now the task is to figure out exactly how often and under what conditions that happened. Subscribe